Okay, time to get started. First, a couple of quick things. First of all, don't forget about the attendance quiz. Here's the attendance code. Don't forget Canvas, the quiz for today's date, and all that. Second of all, I apologize for the heat in the room. This was news to me as of this morning. The AC you can hear is running, but I don't really think it's doing very much. I kind of suspect there's something wrong with the thermostat. It's possible there's something wrong with the AC itself. I have called it into maintenance. You think you find it uncomfortable. I'm up here moving around and stuff. I'm very interested in getting this situation resolved. I'll keep you up to date, but we'll just have to wait and see when they can get to it. Okay, all right. So last time we were talking about Section 3.1. We had just started with Section 3.1, and we made the observation that for a parametric curve, that's the derivative matrix, and we started to think about how that relates to what you might call the single variable derivative of a parametric curve, which, I mean, it is a function of a single variable. And when this is a single variable here, I mean, why can't you talk about the single variable derivative? The only concern is, am I dividing by like a vector or something? That wouldn't make any sense. But nope, that's a scalar because it's a single variable. And so there's nothing that goes wrong with this definition. Okay. All right. So as you might expect, you look at points like this and this. You notice that the line between them is a secant line. That sounds familiar. That's just like something that we said when we were talking about single variable calculus, when y'all were learning single variable calculus. And then as h approaches 0, that secant line gets closer and closer to a tangent line, right? And so you can persuade yourself that this vector will point in the direction tangent to the curve, or you might say it points in the direction that the curve is going, right? And keep in mind, a parametric curve, we have position as a function of time. There is a thing moving around, right, on that parametric curve. And this is literally pointing in the direction that it's going. The other thing you can notice is that in terms of magnitude, if you're interested in the magnitude of this single variable derivative, the magnitude of the numerator is distance. And the magnitude of the denominator is elapsed time between those 2 points. It's literally distance per unit time. It's literally speed. Right? So altogether then, this thing is a vector that points in the direction you're going, and the magnitude is the speed, and that's the definition of velocity. Right? So it's a really nice conclusion, really convenient interpretation. When you're talking about a parametric curve, derivative just means velocity vector. It's kind of awesome. So by the way, reminder, there's lots of different interpretations of calculus in a multivariable context. It depends very heavily on what kind of a picture you're looking at. We've talked about the calculus of graphs. This is not that. This is not a graph, right? We've talked about the calculus of level sets. Not what we're doing here, right? This is the calculus of parametric curves, sort of our first little bit in the calculus of parametric curves. Okay. Alrighty. Now I have a really nice example. This is just cool. It's arguably a digression, but I think it's actually a pretty easy example. You can see there's nothing tricky happening here. And it's really cool when you get a cool callback. It turns out that sometimes you can use multivariable calculus to much more easily draw conclusions that previously were quite a bit of trouble in single variable calculus. And that's what's going on here. So let's just talk about the unit circle. Right? Y'all know the unit circle. Y'all know the unit circle is how we define trig, or said differently, this curve here traces out the unit circle. By the way, it has speed equal to 1 because notice that my parameter, which I'm thinking of as time, is also distance. That's the definition of when you're talking about sine and cosine, the argument is the distance along the unit circle. Right? So if time and distance are equal, then distance per unit time is 1. So we have a unit speed parametric curve. We also know that the velocity is a tangent vector, so it's like that. And the geometry of the circle we know, so we know that this tangent vector, which by the way we know has length 1 because it's unit speed, and this position vector, which by the way we know has length 1 because it's a unit circle. Okay. Unit circle being what it is, these are perpendicular to each other, right? That makes these two triangles congruent triangles. And then just a little bit of geometry. I mean, I totally know the coordinates of that. I totally know what that vector is. That's that right there. And then a little bit of geometry can persuade you that the velocity is this right here. Okay, now we're just working out a little bit of geometry. So what? Who cares? What does this buy us? Well, the point is the velocity is the derivative. If the velocity is the derivative, that means that this purple curve, if I take its derivative, indicated in red, then I get the dark blue derivative vector. And check it out. Just by making a couple of geometric observations, I've now demonstrated that the derivative of sine is cosine, and the derivative of cosine is negative sine. Right? If you think back to, okay, how did this get proved back in single variable calculus? Well, I mean, you write out the definition and you factor some things out, angle addition formulas, you make arguments, you end up with certain limits that you have to show that certain limits are equal to 1 or 0 or what have you. So it's a little bit, it's not that it's that bad, but it's, I'm going to call it unsatisfying, maybe a little opaque, right? I like the fact that this is purely a simple geometry argument, and that to me makes this very satisfying, right? Again, one of the big things I'm always on the lookout for, this is just a personal statement in terms of how do I decide how much I appreciate a mathematical concept. It's one thing if it helps me understand that something is true, and it's yet another thing if it helps me feel like I understand why it should be true. And I feel like this gives me a really nice should. Does that make sense to everybody? Okay. Digression, but I think fun. Okay, let's kind of do a more computational example here. Suppose I give you a velocity as a function of time, and the questions are going to be how do you compute the acceleration and how do you compute the position. And no big deal. We argued on the previous page. Anyway, acceleration is the derivative of velocity, and position is the antiderivative of velocity. Right? If velocity is the derivative of position, then position is the antiderivative of velocity. I'm sure you all have made that argument in a single variable calculus setting previously. Is that cool? Just to get the ball rolling? All right, so the computations are pretty straightforward. By the way, good news. How do you take derivatives? Well, you do it one coordinate at a time. Nice and easy. Likewise, how do you take antiderivatives? Well, you do it one coordinate at a time, just like you would hope. Right? Very convenient. And don't forget your single variable calculus. By the way, reminder, single variable calculus is in the prerequisite trail of this class. So we are going to assume that you are proficient with, I'm going to say, standard single variable calculus stuff. So derivative rules, so pretty much all the derivative rules, I think there's nothing that really obscure there. With the antiderivatives, all of the non-obscure antiderivative rules. So for example, obviously power rule, trig rules. So integration by parts is very standard, and substitutions very standard. Right? So do make sure that you're really good at those. You're going to have to be able to crank those out reliably. And just as a reminder, I think I've said this before. I can never remember what I've said in which class. The Pratt School of Engineering has specifically ask the math department. Make sure to keep these students up on their single variable calculus because we need them to be good at single variable integrals, right? So we keep getting that request from the engineering school, and so that's one of the reasons, it's not the only, but it's one of the reasons that we keep, yes, you are going to have to do some single variable integrals, yes.
Should we know the inverse trig?
You mean stuff like let's see, the integral of like 1 over the square root of 1 minus x squared, stuff like that?
Yeah.
I probably wouldn't worry about that. I mean, yeah, it's not a bad thing to know, but I wouldn't lose any sleep over it. And on an exam, I would probably try to, I'm not making any promises, but I would probably try to avoid putting you into that circumstance. Now I will say on an exam, if you've got some problem, whatever it might be, and you get it down to, at the very end, you just have to compute this integral and you just can't compute that integral, then just be honest and just say, okay, I don't remember how to do this integral, right? And everything you did before, you get partial credit on, and how important will that integration be? It'll be something, but it won't be everything. Yeah. Okay, don't forget about the integration constant. Easy to mess that up. And by the way, make sure that you are clear on the following. The integration constant and the initial condition are not always equal. A lot of students are under the dramatically false impression that these are always equal. They absolutely are not. Let me show you how easy it is to see that they are not. The way we evaluate C is we look at this equation. R is equal to that plus C. We plug in T equals 0. Plugging T equals 0 turns that into that. Plugging T equals 0, a little bit of arithmetic turns that into that. And then of course C comes along for the ride. And then this equation, very easy to solve for C. There it is. And it is not the initial condition. Right? Is that everybody see that? Okay. So two things about this. If you are under the mistaken impression that the integration constant is always equal to this, which I can't emphasize enough, not true. For one thing, you're going to get some wrong answers. But as I always say, it's not a course about answers. Right? The bigger problem than getting the wrong answer is that it's invalid reasoning. That's the real problem. Right? So now let's try to talk about where does this misunderstanding come from. Well, very often these functions, that's not the color I wanted. These functions that were the givens in high school calculus classes, very often these will always be polynomials. And if those are polynomials, then the antiderivative will be polynomials where every factor has a factor of t. And then when you plug in t equals 0, when you plug in t equals 0, this will then always turn into all zeros. And so, of course, if these end up being zeros, if this ends up being a 0, well then yeah, it's going to turn, in such a case, coincidentally, it will turn out that the integration constant will be the initial value. That is a coincidence. It's a peculiarity based on the fact that some high schools only use polynomials. Right? So, bad examples, basically. Anyway, make sure that you are not under the false impression, and make sure to do the appropriate computation to evaluate your integration constants. Okay, real quick reference. The rest of section 3.1 well, much of the rest of 3.1 is a bunch of analysis of Kepler's computations related to planetary motion. It's cool math. It's historically interesting, right? There's powerful stories there. Big ideas. Wonderful stuff. Very cool. And we don't have time for that in this class, unfortunately. So you're not responsible for that stuff, except you do need this proposition 1.4 right here. It's no big deal. It's just a couple of formulas. Basically a couple of product rules. If you have a couple of vector valued functions and you dot them or cross them and then take a derivative, right? So in both cases, derivatives of a product of sorts. And notice in both cases, you get product rules. It's exactly what you would expect and hope based on how we write it down. So I'm going to call these good news, but do make sure that you're aware of them, and everything else in the Kepler area you're not responsible for. Okay. All right, so that finishes 3.1. Moving on to the chain rule. So I'm going to start with the single variable chain rule. I know that y'all are good at the single variable chain rule. I'm not going to try to teach you the single variable chain rule. I have a particular incentive here to talk about the single variable chain rule. I want to get us on board with a particular, very specific, narrow take on the single variable chain rule. Because this very specific take on the single variable chain rule will adapt to the multivariable setting extremely easily, right? So this is a segue. Think of this as a stepping stone. We're going to look at the single variable chain rule a certain way so that we can do the same for multivariable. All right, so that said, this may or may not be your favorite way to think about derivatives. Doesn't matter. This is what we need for this purpose. The derivative is what you multiply by input velocity to get output velocity. Again, there's a million different ways to think about single variable derivatives. This is the one that we're going to need here. So let's just make sure to be really comfortable with this. The derivative is the factor. It's a multiplicative factor that you multiply by green to get blue. Is that cool? Is everybody on board with that take on derivative? Okay. All right. So, chain rule, of course, is about compositions. By the way, I have a bunch of stuff on the page here that ultimately we're not going to use at all. So this is arguably a distraction. I'm actually thinking about removing that stuff. Basically, I'm going to do a hand-wavy kind of intuitive argument as to why things go as I claim. I think it's actually very satisfying. I think this algebra is ultimately a distraction. So anyway, let me just kind of cross that out. You can look at it if you like. It doesn't matter. Anyway, what we have here, we have a single variable function, where y is a function of x. We have a subsequent single variable function, where z is a function of y. All right. So what comes out of the first function is what goes in to the second function. That's how compositions work. And then there is a third single variable function. The third single variable function like this. It's the composition where z is a function of x, sort of by way of sort of doing f first and then g. Is that cool? Everybody remembers compositions? Okay. All right, so here's the thing. If you are at some point A, if you're moving with some velocity x prime, your image here will be moving with some velocity y prime. Y leads to z. Z will be moving with some velocity z prime. I have these three velocities, right? And I claim that we can write down certain relationships between them. And they are just this observation up here. The observation is that a derivative is a factor. It's what you multiply, right? So taking that take down here, I'm going to represent f prime as being that factor. It's what you multiply by x prime to get y prime. But again, just think of it as it's a factor that goes from there to there. Whereas g prime on this picture, well, it's the factor. It's what you multiply by y prime to get z prime. I missed. Y prime to get z prime. So it's that factor from there to there. Okay, and now on this picture, where's the derivative of the composition? Well, it's this factor that you multiply by x prime to get z prime. Now again, we're just looking at three functions. Each function has a derivative. Each derivative is a factor. Is that cool? All right. Okay, well, so the derivative of the composite, this purple factor that I'm looking at, it's what you multiply by x prime to get z prime. But here's another way to think about it. What am I doing to x prime? Well, I'm multiplying by dy dx, and then I'm subsequently multiplying by dz dy. I'm multiplying by one factor, then I'm multiplying by another factor. When you multiply by a factor and then another factor, altogether you multiply by the product of those factors. Factors multiply. Right? Does that make sense? Everybody happy with that? If I give you some value and say, here, multiply by 2, and now multiply by 3, altogether you've multiplied by 6, because 6 is 2 times 3. That's all we're talking about. Factors multiply. Okay, well, that does it. If factors multiply, the overall factor is the product of the two individual factors, and there's your single variable chain rule right there. All right, is that cool? Now again, maybe not your favorite take, and again, don't worry about, we don't really need any of that. Maybe you've got a different way you like to think of the single variable chain rule. Fine, no problem, but we need to think about this one, right? Again, the upshot here, all I'm saying is that a succession of factors multiply to give the overall factor. Okay, that's all I'm going to say about the single variable chain. Well, I'm going to come back in a couple of little micro points. But this single variable chain rule, this take on the single variable chain rule, allows us to do a totally analogous thing in the multivariable setting. This is going to be a shameless ripoff of what we just did. All the same ideas, just multivariable. So we'll start with, how can I think about, how can I think about a derivative? Keep in mind now a derivative is a matrix. How can I think about that? Well, it's what you multiply by input velocity to get output velocity. This is one of our, initial points of view, one of our first points of view on how to think about a derivative matrix. It's what you multiply by input velocity to get output velocity. It's the factor. Wrong color. It's a factor. Just like it was in single variable on the last page, right? I'm taking the same analogous take on multivariable derivatives as we did on single variable derivatives. It's a factor. Now, it's a little weird. Back here, it was a factor, but it was a scalar multiplying by a scalar to give another scalar, and maybe you're accustomed to thinking of factors as being scalar factors, and it doesn't have to be. This is a factor in the sense that a matrix multiplied by a vector gives another vector. It's still something you multiply, it's still a factor. Is that okay for everybody? Everybody buying it? Right. So, okay then, and again, it kind of ignore the unnecessary, we're not going to need this or that. Let's just look at composition of functions here. Here is a multivariable function. The input variables are x1 and x2, output variables y1 and y2. here is a subsequent multivariable function. The inputs are y1 and y2. The outputs are z1 and z2. So two multivariable functions, and I'm composing, and hopefully no surprise, the third multivariable function we're going to talk about is the one like this. That's the composition. Inputs are x's, outputs are z's. Where we do f first and then g second. Cool? Well, you might be able to see this coming on this picture. df is the factor that you multiply by x prime to get y prime. So again, let's not, don't get lost in the weeds of the algebra, but df is a factor that takes you from here to here. dg, likewise, is a factor that takes you from there to there. And factors multiply. Right? Whatever it is that we started with, whatever this x prime is, multiplying by df, and then subsequently multiplying by dg, altogether we've multiplied by the product of those matrices. And so altogether, the factor that you multiply by x prime to get z prime, altogether then, the derivative of the composition is the product of the individual derivatives df and dg. What do you think? Yeah, and again, don't ignore the algebra that we don't. All that algebra is just kind of an algebraic version of what I think is just more easily understood as factors multiplying. Everybody buying it? I think the analogy is very, very strong. So look at what we've got here. Look at what we've got back here. It's the same argument, just apply it in a different context. So I hope you find that compelling. This is my favorite take on the multivariable chain. Okay. All right, I'm going to leave that there. So a couple of quickie things. Let's see here. You'll notice that we started with a composition, G compose F, and what we ended up with was a product. We're specifically multiplying the individual product matrices. So I like this pithy little phrase that I have here, differentiation turns a composition into a product. I think that rolls off the tongue really nicely. Ultimately, that's all the chain rule, the matrix form of the chain rule says. Differentiation turns compositions into products. That's the whole story. Okay. All right. Another little detail worth mentioning. It doesn't matter what dimensions you're talking about. Now, if you look at the picture that I drew here, this picture specifically, I drew this as being two-dimensional, and I drew this as being two-dimensional, and I drew this as being two-dimensional. Did you notice nowhere in the argument do I make any reference to the dimension? So I tell you what, I'm going to make a couple of these three-dimensional now, and okay, boom, Y3. Okay, now it's a three-dimensional second space, and let's make the third one three-dimensional as well, Z3. Okay, so now seemingly a new chain rule, right, where it goes from 2 to 3 to 3. Whatever, right? No matter the dimensions, DF, if it goes from 2 dimensions to 3 dimensions, all that means is DF is a different shaped matrix, but it's still a matrix that turns this vector, 2-dimensional, whatever, into this vector, 3-dimensional, whatever, who cares? DF is the matrix that does that, independent of the dimensions. The only thing that changes is the matrix will be a different shape matrix. Yeah?
Is GOF standard notation, or are there other ways?
Yeah, I hear you. So that does look like an O, doesn't it? But it's actually just a tiny little circle. Okay. So using a circle to represent a composition is pretty standard. Yeah, but yeah. So I'm sorry. It's just really hard to distinguish a small circle from a small O. Yeah. Okay. Anybody else? All right. Okay. So yeah, dimensions don't matter. Okay. Last little detail I want to point out. Easy to mess up. This is something that used to confuse me long ago. Let me just remind you, input velocity, output velocity, the derivative, derivative matrix is the factor that I multiply. So here's the thing, the derivative matrix is made up of a bunch of partials. Partials are functions. Where do I evaluate these functions? Right, df evaluated at what point? And I'm going to say, hopefully this is satisfying. When you're doing calculus and you're taking a derivative, you take the derivative and you evaluate it at the point where you're at in the domain. That's how derivatives work. So we're at this point, A. So the derivative is evaluated at that point A. Is that pretty believable? Is everybody on board with that? All right, so keeping that in mind, we evaluate at the point in the domain where we're at, from which we're moving with whatever velocity. Well, if you apply that to this result here, notice for this function, g, where we're at is not A. Where we're at is f of A. That's just where that function is. I mean, that's where we are when we're plugging into this function. If you're plugging into the g function, what you're plugging in is various different values of y. You're plugging in a point in this y space. That point in the y space is the outcome and the output from f where you put in A. In other words, this point is f of A. So dg is evaluated at f of A. Does everybody buy that also? You may even remember something kind of like this from the single variable chain rule, what they used to call Newton's version of the single variable chain rule. All right, so something else to keep in mind. Okay, is everybody happy with all this before we do an example? Example incoming. All right, here we go. Here's a couple of functions that we're going to compose. Very conveniently, you'll notice that the variables that are coming out of the first function are the variables that go into the second function. They better be, because we're composing, and that's how composing works. What comes out of the first goes into the second. Right? So it's set up conveniently prepared for composing. You'll notice we don't have the formulas for these functions. I'm not telling you what these functions are as formulas. I'm just giving you certain specific details about these functions. The question is to figure out what is the derivative of the composition at the point 1, 2. And conveniently, this is set up just perfectly. I mean, I can just copy from the previous page, derivative of the compositions, the product of the derivatives. So we just write that down immediately. And further details, of course, to follow. But is everybody good here so far? Let me point something that could have been confusing. Lucky break. The way I wrote down the matrix form of the chain rule, I wrote it down as G compose F. Won't always be. Sometimes you might be looking at F compose G. Sometimes you might be looking at Q compose Aleph. Right? Who knows? Right? So it won't always necessarily be exactly these same letters, but you got to keep track then of, wait a minute, which one is applying first and which one is applying second. And you got to be real careful about this. Notice in the diagram, it's easy to get this wrong. the function that acts first is f. In the diagram, f is on the left. But in the composition, f is on the right. And in the matrix product, df is on the right. Even though in the diagram it's on the left. Everybody see that? So be careful about that. It's really easy to kind of carelessly just kind of always put the letters in the same order as if that matters. And that's a huge liability. You should always think not about left and right, think about first and second. Right? When you're composing functions, that's first and that's second. When you're laying them out in a diagram. When you're writing it out as algebra, the one on the right is first, the one on the left is second. When you multiply matrices, the one on the right is first, the one on the left is second. And the reason for that, of course, is that the what you're putting in, what you're multiplying by, is on the left in the diagram, but it's on the right in terms of how matrices multiply by vectors. Right? So again, abandon this whole left-right thing. That's a red herring. That's a distraction. Always think in terms of which one's acting first, and that is always the same across all of these contexts. Okay. Alrighty. Yeah, so we wrote this down, and let's see, conveniently, some of what we need, we're just looking at it here. DF at 1, 2, right? I needed that. Boom, I have it. Bam, there it is, plugged in. Cool, done. Let's see, the next thing I need DG at the point F of 1, 2. Not immediately clear that that's what I have. I have DG at 310, but notice 310 is F of 1, 2. And so DG at F of 1, 2 is DG at 310, which I have. How we doing? Everybody with me? Feel free if you have questions. And then you multiply the matrices. Y'all know how to multiply matrices. Okay. I will point out, and so some people might think of this as being a dirty trick. It's not. This is a deliberate tool for distinguishing between. There's two different ways to approach this class, right? There's two different kinds of students. You might say there are students who understand the ideas and think things through to make sure that their work reflects how the ideas fit together, right? And then there are students who kind of notice patterns and make inappropriate assumptions, etc. Right? So make sure to be the former type, not the latter. You will notice that where I gave the matrices, come on, colors. You had to kind of switcheroo. Right? Now, the way we approach the problem, right? We write down the chain rule, we think carefully about the order, first and second, all appropriate, and then we put what we need where it needs to be, and there's no tricky curves on this. Right? There was nothing hard about it. We just have to, again, think through what's first, what's second, and do the right thing. If you're careless, if you're not thinking through the details, the casual, sloppy take on this would be, the derivative of composition is the product of the derivative matrices. I'll just multiply these matrices together. And you see, you get them in the wrong order if you're not careful thinking through the specifics. Does everybody see what I'm talking about there? So these details do matter, and you do have to think that through. That is part of the material that makes this work, is you have to get these matrices in the correct order. So make sure that you think that through. It's an important detail. Okay. All right, now the next part of the questions, we've answered that. We've computed that derivative matrix. Next part of the question, compute this specific partial derivative Thinking of z's as functions of the x's, notice that's part of the composition. Right? How you turn the original inputs into the eventual outputs. And let's just think it through here. Well, let's see. We're taking a partial with respect to x1. Here's x1. It's the first input. Inputs, got to remember from chapter 2. Well, we're still in chapter. From earlier in chapter 2, input variables correspond to columns of the derivative matrix. So because that's the first input, we're going to look in the first column of our derivative matrix. Let's see here. We're taking the partial of Z3. That's the third output. Outputs correspond to rows of the derivative matrix. Everybody remember that? It corresponds to rows, right? So third output, we pick the third row. And what we need then is that element of the derivative matrix we just computed. So that partial derivative is 3. What do you think? Okay. Alrighty. Couple of special cases. These I'm going to be really quick. They are pretty straight read, but I like to hit the highlights on these things. First special case, what happens when you have only one variable as the original input variable? Sort of a one-dimensional original domain. And, well, there's a couple of consequences to this. Keep in mind, input variables correspond to columns. If you only have one variable, one input variable, as this function has only one input variable, the derivative matrix is only going to have one column. The composition has only one input variable, and therefore its derivative matrix has only one column. By the way, notice further, these two functions, the green and the purple, let's see, the green one gives position in Rn as a function of time. That's a parametric curve. Derivatives of parametric curves we know are velocities. So this is literally the velocity vector in Rn. Likewise, the purple function, the composition, that gives position in Rm as a function of time. That too is a parametric curve. This is literally the velocity of the output in Rm. So what we have then, really nice sort of conclusion, is we have a sort of a confirmation of how to think about the derivative of this function f. The derivative matrix of f, according to the chain rule, again, all I did is write down the chain rule. The chain rule is telling me that the derivative matrix for f is what I multiply by my velocity in the domain to get the velocity in the target. And we already knew that. Right? This is one of our primary interpretations of, what does a derivative matrix do? A derivative matrix multiplies by input velocities to give you output velocities. So I think it's kind of great when stuff like this happens. Our brand new chain rule is kind of a generalization, in a sense, of this old fact about derivative matrices. So anyway, kind of fun. You'll notice that this example here is nothing more than just kind of putting that into action. Let's see here. We have an input velocity given. The question is to find an output velocity And so how do we do it? What's the procedure? How do we answer this question? Well, derivative matrix is what you multiply by the input velocity to get the output velocity. So you compute the derivative matrix and multiply it out. So just an immediate application of this special case. And again, by the way, this is an immediate application of an idea we talked about in section 2.3. Right? So old news. I have literally thought about taking this example and copy, cut and paste back into section 2.3, but I kind of like having it as sort of a demonstration. And I don't know, for whatever reason, I like it here better than section 2.3, but it fits in either place. Okay. Same sort of a deal here. And again, I'm going to be very quick, and y'all should read through the details as noted there. But if you also, in addition to having only one input, if you also have only one output, eventual output, outputs correspond to rows. One output means this derivative matrix has one row, and that means that I can realize that matrix product as a dot product with the gradient. So old news, right? And again, this is all the partial derivatives of y with respect to all of the x variables. That's literally the definition of the gradient. And this matrix vector product is morally the same as a vector dot product. Again, we saw that back in section 2.3. So nothing new here, just sort of a, it showed up again, and I think it's worth noting that it showed up again. How we doing? Is everybody with me? All right. Okay, a new point of view. This is definitely different. Sometimes you're only interested in one single partial derivative. Now, the derivative, the matrix form of the chain rule is this whole thing. This is all together when you have, one function and you write down its entire derivative matrix, and then you compose with a subsequent function, you write down its entire derivative matrix, then the derivative of the composition is the product of those individual derivative matrices. So again, it's just the matrix form of the chain rule. We already wrote that down. Nothing new yet. But sometimes, if you are only interested in just that one partial and you don't care about the rest of all of this stuff, don't need it, right? You just want to know just this one partial derivative, it can be really convenient to notice that you can compute that one entry just by looking at just that row, just the corresponding row of the left matrix, and correspondingly just the corresponding column of the right matrix. And when you sort of do the resulting dot product, the thing you're interested in is going to be a literal dot product of this blue row with this green column. And so you get this formula right here. So if you want to understand the entire derivative, right, the complete, the biggest, the most general, most powerful version of the chain rule, well, it's this right here. It's the matrix version. Oh my gosh, for sure. Right? But if you just want one element, you only need this one little formula. Pretty good? Okay, so you might call this a coordinate version of the chain rule, perhaps. Very handy. Now, we're not going to have time to do much with this, but I do want to warn you about one thing. This is a real big problem. I see a lot of students messing this up. It's catastrophic, and it's easily addressed as follows. Here's what a lot of students do. A lot of students will start writing this down, and they get to about here, and then they think, oh my God, hey, check this out. That and that, I feel like those cancel. And then notice that is exactly this, and that is exactly that, and oh my God, I think we're there. I think we're done. I think maybe this is all I need. Maybe this is unnecessary. Right? Everybody see the allure of that? Okay, this is catastrophically wrong. Now, one way we know it's wrong is we already multiplied out the matrices. This is how matrices multiply. This stuff is there. That is the formula, and you can't just stop writing down the formula because you feel like it, right? So we know we get a wrong answer with this nonsensical reasoning, but what's wrong with the reasoning? Why don't these cancel? And the reason they don't cancel is because they're not the same things. The notation is fatally flawed. These two things, we're writing them as if they're a well-defined thing, and they're not. This first one represents how much y changes in a scenario where most of the other y variables have to be constant. That's a completely different scenario from what's going on. This represents how much y changes, but in a scenario where all the other y variables are probably changing. Because xj is changing, all these other y variables are functions of xj, and so this is just a completely different scenario. The analogy that I like here is, let's see if I can get it right. My daughter just this morning was watching one of the Spider-Man movies, and there's a character named Harry, right? Good movies, by the way. But there's a character named Harry. She also likes the Harry Potter movies. There's a character named Harry in that movie. These are not the same people. Right? They have the same name. They're not the same people. They're totally different stories. You can't just say that they're the same. That's what we're looking at here. These both represent how much y changes. We use the same notation for them, but in completely different scenarios where there's totally different things happening, these are not the same. You can't cancel them. So this cancellation up here betrays a fundamental misunderstanding of what this notation means and how the chain rule works. Make sure you don't make that mistake. You cannot do that cancellation. Sorry to go a little over. This is a good stopping point. Picking up here on Monday. Y'all have a great weekend. See you later. Thank you. Yeah, see you later.